Hello, and welcome back to another exciting lecture in the wonderful world of material science and BCIT's TTED 3044 class. Today we're going to look really close inside a piece of steel. We're going to get closer and closer and closer, and I'm pretty sure I can't put that drill bit in there close enough that you can see the steel at an atomic level, but we're going to be taking a look at steel at an atomic level. And specifically, we're going to be taking a look at the iron and the carbon at an atomic level and how those two atoms behave as you heat the steel and then as you gently cool the steel. So without further ado, let's take a look at some of the terms that you're going to have to understand. Now, you're going to hear me refer to a couple of words like austenite and ferrite, a body-centered cubic, and face-centered cubic quite a bit. And it helps to understand a little bit what we're talking about because I'm going to throw other words in there like interstitial voids and anyway, just stick with me. We'll walk you through it, and we'll come up with a whole bunch of new words to add to your vocabulary list for this class. Now, what we're going to talk about right now is face-centered cubic and body-centered cubic crystal structures. In some of our previous labs, we've looked at the fact that metals are made up of tiny little crystals, and the little crystals are bonded together using metallic bonding, which is a way of bonding atoms together where they kind of share all of their electrons together in one big cloud of electrons, and that's why metals are such good conductors of electricity and heat mostly. So what we've got in there is we've got all of these atoms bound together, but they'll only arrange themselves in certain orders. And most of the time that depends on what atom you're trying to arrange. So we're going to take a look at the iron atom right now. And when you arrange it in certain ways, you can do certain things with it. Anyway, stick with me here. We need to understand the concept of body-centered cubic and face-centered cubic because they're two different arrangements of iron atoms. For both of them, you start with a cube. That's where the cubic bit comes from. Now you put some atoms on the corner of the cube. Okay, so you can see that we've got some iron atoms right there sitting on the corner of the cubes. Now I've just drawn the nucleus of the iron atoms in right there, just the center points of those atoms. And this creates something that we call a cubic crystal lattice. Now, if you had a whole bunch of cubic crystal lattices, then you'd be able to form a crystal out of that structure. And some atoms do naturally form pure cubic crystal lattices. However, a body-centered cubic crystal structure will also tuck one atom into the middle. Okay, so we've got a cube, and tucked in the middle, we've got another atom in there. So this is our body-centered cubic crystal structure, and this is the form that iron is in below 723 degrees Celsius. We're going to come back to that 723 degrees Celsius quite a bit, and a little bit later on I'm going to show you a phase diagram that shows you why it's so important. And this type of iron at the low temperature, so all the iron you see at room temperature is known as ferrite. Another term that I don't use that often, but you'll see used in some textbooks and some references is alpha iron. Okay, so low temperatures, anything below 723 degrees is low temperature. We're not talking freezing here. Anything that's not glowing hot. Okay, let's phrase it that way. If it's not glowing hot, then you're looking and you're looking at a piece of steel. Somewhere in there, you're looking at some ferrite. Now, let's go back to that structure and see where carbon comes into play in this, because right now I'm only talking about a pure iron structure. And so if we add electrons around those nuclei, so the electrons form a shell, and it kind of makes this look like a ball. Really what we're doing is we're stacking balls together here. And if we add those electrons in, and then we say, okay, well, the corner ones are shared between, the corner atoms are shared between a couple of cells. Let's cut this down, and let's take a look at one unit cell. So you can see on the corners, we've got on the top level, there's 4 atoms there, and we're actually seeing sort of 1/8, I guess that would be, of each of them. And on the bottom, there's 4 more, and we're seeing 1/8 of each of them. And right smack in the middle, hidden in the midst of all that, is one more that we can't quite see glowing away in there. I had a lot of fun putting this together in 3D animation software, adding in some of the special effects. Now, we cut that down, so there's a unit cell, and if we take a lot of those unit cells and place them together, we'll end up with a crystal. I think somewhere in here I'm supposed to be getting many of them coming together. Anyway, I thought that we were going to get big growth on the crystal in there. That must have been a different animation. So there's empty spaces inside that crystal. So if you think about throwing a whole bunch of basketballs into one of those basketball trolleys that you see down in the gym class, or stacking bowling balls on the wall or something like that, there's empty spaces in between the balls. There's empty spaces in between these atoms. Yeah, now we're talking atomic size spaces here, right? It's not like you're going to pass your finger through these spaces. So, but there are these empty spaces called interstitial voids. And you can actually take a small atom and you can fit it into those voids. But in ferrite, carbon's just a little too big to fit into those voids. So ferrite can only hold like 0.008% carbon by weight. So you'll recall like a 1020 steel would be 0.2% carbon by weight. So you can hold about 1/20th, less than 1/20th of the steel in a 1020 steel in the interstitial voids of the ferrite. So basically, when we talk pure ferrite, we're talking pure iron. And if you have more carbon than that, then we get into another formulation, and that's Fe3C. Now, Fe3C is not actually a metal. Fe3C has the iron, but it's not metallically bonded to the carbon in that case. It's covalently bonded. So you've got this structure that forms in there, and it's a hard and brittle, almost ceramic-like structure called cementite that's going to form in there. So if we've got more carbon than can be absorbed by the ferrite, which is essentially none, then anything that's left is going to form into this hard and brittle material that's going to get distributed throughout the microstructure. So here you can see the voids, and I've put some carbon atoms in there, but really they don't fit. They run into the electron clouds and they get squeezed out. There's just no room for them. You can fit 1 or 2 in by kind of stretching some of the bonds, but not into a unit cell. They'd be distributed across many, many cells. So ferrite doesn't really hold much in the way of carbon. I've drawn it in there, but it's not in there. That's where it wants to go, but it can't fit. However, when you heat your iron up and you get above that 723-degree range, and this is right at about the point where your iron starts to grow a dull cherry red, we call it. So you've seen that when you're doing some of your gas welding, working with the torches down there. In fact, you get way beyond that when you do your arc welding and you're melting the actual steel. So when the iron heats up above 723 degrees, we start to see some changes. And it's a really important transition because the entire crystal structure changes. And it takes a little while to do, and it takes a lot of energy. It's as big a deal as melting or evaporating. Okay, because melting and evaporating are just phase changes. You're going from, when you melt, you're going from a solid to a liquid. When you evaporate, you're going from a liquid to a gas. Those phase changes are a big deal. Going from ferrite to what we're going to tell you is now called austenite by changing the crystal structure is also a really big deal. And our ability to do this and control this is what makes iron so useful. This is where all the real hardening happens to come in steel. So this new phase that we're going to be talking about is called austenite. And if you, like I say, sometimes you hear ferrite referred to as alpha iron. You'll sometimes hear austenite referred to as gamma iron. And austenite has a face-centered cubic crystal structure. So we had a body-centered cubic at low temperature. We're going to have face-centered cubic at high temperature. And there's some other names for a face-centered cubic structure. So if you're looking up your crystal structures list, because this is all out there online, of course, and FCC will also be referred to as CCP or cubic closest packed. It's a really good arrangement for atoms. But one of the interesting things that happens is that it has bigger void spaces. So remember I was saying that the carbon didn't really fit into the interstitial voids in the ferrite. In the austenite, we're going to be able to tuck it in because in face-centered cubic, the structure is a little bit different. Again, you start with a cube, but instead of adding one atom to the middle, the atoms slot in on the faces. So here we've got a unit cell coming together. And in our unit cell right here, we've got the FCC unit cell. We've got a half of an atom right here, a half of an atom right here, a half of an atom right here. 1, 2, 3, 4. That's going to be 4 times 1/8 of an atom, another 4/8 of an atom right down on that corner. And you can add it all up and you get a total number of atoms per unit cell. But what you'll notice right in here is that this gap is a little bit larger and this gap is a little bit larger than it was on the body-centered cubic cell, and these are the interstitial voids that can fit the carbon atoms. So the carbon atoms slip right in here, and what you're able to do, it's like throwing baseballs into that bucket of basketballs. Okay, you can actually fit the baseballs in between the basketballs without having to rearrange the basketballs. Now you couldn't do that with the arrangement that we had at the lower temperature. But here, when we heat everything up, the carbon is able to diffuse evenly and shake around and fit itself into those voids. Now, that's really important because there's space now for up to 2% carbon by weight to diffuse evenly throughout the steel and give you a uniform microstructure of 100% austenite when you're up at high temperatures. This stage where you've heated up all of the material into austenite and have the carbon evenly diffused across all of those interstitial voids that makes steel magical. So just take a quick look right here. And there is our ferrite trying to fit carbon in there, and you really can't do it. There's not enough space for that carbon atom to fit nicely. But in the austenite, there's all these places in between the various balls, in between the various big iron atoms, where you can fit in the small carbon atoms. So I wanted to go through that and give you a couple of slides on some terminology. Body-centered cubic is our ferrite. It's the low temperature form of steel. Face-centered cubic is the high temperature form of steel, and we call it austenite. The difference between the two is important because austenite can hold a whole bunch of carbon in interstitial voids, keeping it in solution, while ferrite cannot. So when you heat up your steel, you can evenly distribute all of the carbon. But when you cool it down, interesting things start to happen. So that's the next deck of slides here. So let me just close this one and move on. So this sets us up for talking about the iron-carbon phase diagram. And if you've got access to my source file for this, I've tried to stick to using publicly available images and materials. And where I have used somebody else's work, you can link to it by clicking on the hyperlink. So some of these images that you'll see in here are not my own. So What is a phase? Well, we just spent some time talking about that, and we talked about two major phases that we care about. But really, phases exist for all different materials. So, very common ones that we see with water, we've got a solid phase that we call ice, a liquid phase that we call water, and a gaseous phase that we call steam. And water really only has those three phases. And you can certainly get iron solid that we see all the time. You can get iron liquid, molten iron, when you're welding or casting steel. You can even get gaseous iron if you keep heating it up even higher than the melting point, and it starts to get liquid and flow and run, and now all of a sudden you're getting hotter and hotter, and those atoms are shaking around in there even more, and a few start breaking free. You can get gaseous iron. But in between well, I shouldn't say in between the low temperature and the high temperature, before you melt your iron, you actually go through a couple of different solid state phases. And the two we're concerned about are the ones that we were just talking about with the other images. And below 723 degrees, we've got ferrite, and above 723, it's austenite. Now, like I say, we're not changing from a solid to a liquid. We're just changing the crystal structure in here. But it's just as important and just a big deal, in some ways more important than switching from a solid to a liquid, because it really lets us do a whole bunch of interesting things in the steel. So you're going to know you're approaching this temperature. You'll see a dull red as you heat materials up. That's about 550 C. As it starts to get to this dull cherry red, it will be glowing about the right color there. And we'll usually heat it up into this range where we're seeing some brighter reds in here. And you don't need to heat it up here to the glowing yellow stage in order to see the phase transformations that we're going to be looking at. Just got to get it nice and warm. Sometimes we'll heat it into the orange range right here. Now, why we're getting the colors off of there is a whole other neat area of physics that I'll talk to you about some other time, probably in electronics, where we're talking about our LEDs. Black body radiation is just amazing, and if I start talking about it now, I'm going to be distracted and we'll never get to the point of this presentation. But yeah, why? Why do things start to glow when you heat them up? We have answers to that, and the answers are pretty cool, actually. So, what is a phase diagram? So, since we just started talking about phases, we may as well talk a little bit about what a phase diagram is. And what that allows us, phase diagram allows us to do, is to take a look at the material and say, well, what happens when we change a concentration of something, and what happens when we change a temperature of something? Because many things in life exist as a solution. There's some pure things out there, but many things are a solution or in some ways an alloy. Now, I would never refer to salt and ice as an alloy. That's definitely a solution. But in this chart right here, on this side, we've got a mixture of 0% salt and 100% pure water. So your pure water runs up and down this line right here. And over on this side, we've got the equivalent set of things, 100% salt and 0% water. Now, if we're back here on the side and we look at pure water, we know a few things about that. We know that it freezes at 0 degrees. Okay, so if we're above 0 degrees and we have a little bit of salt added into the mix right here, then what's going to happen above 0 degrees, we're going to be in this range right here, and it's going to be a salt solution. So it's going to be liquid water with salt dissolved in it. But as we start to come down cooler, in this region, we start to enter what I call the slush zone. And there's far more technical terms for that, but if you just call it the slush zone, then I think that's a really good sign of what's happening, because it's not yet solid. If you come down below minus 21 degrees, then you're going to get solid ice. Doesn't matter how much salt you've put in it, it's going to be solid ice. But in this region right in here, I mean, well, you live in Vancouver, or you've spent a winter in Vancouver at least, and you know what it feels like to go out in the slush. And it's just that miserable, not quite solid, not quite liquid, sticky crud. And that's because there's a lot of salt on our roads, and that creates this slushy zone right in here where the ice isn't quite frozen, but it's not quite liquid either. And as you keep increasing the concentration of salt, the temperature at which it stops being liquid and starts becoming slush keeps going down and down and down. And eventually you'll reach minus 21 degrees Celsius. And at that point, okay, right there, if you drop any colder, then you're just going to have uh, you're just going to have a solid ice. It's going to be salty ice, but it'll be there. And if you add any more salt to it, then the liquid can't sustain any more salt. You've completely saturated the solution. So now you end up getting some solid salt plus the salt solution plus the slush. So this is another slush zone here. But whereas this one's got some pure ice in it, this one's got pure salt in it. So a phase diagram can be used for many common solutions that we see. We could draw another one up and we could have the alcohol water phase diagram, and we could have a temperature come up and down this way, and we could take a look at what temperature your beer chills and what temperature what temperature your beer freezes, what temperature your wine freezes at, what temperature your whiskey freezes at. And then over on this side, you'd have the 100% alcohol, what temperature alcohol freezes at. And we could look at the behaviors all through here for different concentrations of, um, of ethyl alcohol content with water. So there's all sorts of phase diagrams out there, but we're going to take a look at the one that applies specifically to steel. Click, click. Why am I not transitioning my slides? Oh, there we go. Hey, there we go. The iron carbon phase diagram. There we have it right there. It's beautiful. And maybe it's a bit too much too soon. So let's go on to the next slide right here. I have no idea where my windows have gone and why is this not letting me advance things? There, okay. I've got my control. Hey, there we go. Whoa, PowerPoint poisoning. It's getting to me. Friday afternoon. So what we're going to do, that phase diagram that I just laid on you on the previous slide is a lot more information than you actually need to process, and it doesn't apply to a lot of what we're doing. So we're going to take a look at a little bit of a simplified view right here. And really, we're only concerned about steel. Now, over on this side of the chart, outside the yellow zone in here, we're getting into cast irons. So if you're working with cast iron, you're going to be paying attention to this part of the chart because that's also part of the iron carbon phase diagram. And really the difference between having a steel is steels will tend to be less than 2% carbon by weight, because this point right here is at the 2% mark, and your cast irons will be above that because they pass through a whole bunch of other phases, because steel's got more than just the austenite and ferrite. They've got lead barite over here as another phase that you're getting into. So all sorts of interesting things going on. But we're going to take a look at this range right here, and we can further simplify it by restricting our range of temperatures, because nothing really much interesting happens to our steel below about well, this says 410, but the degrees Celsius is right over here. There's our 723 Celsius. Once you're down below, uh, well, even once you're a few degrees below 723, nothing really changes. So this region in here is all just normal room temperature stuff. And when you heat it up, when you start getting up above here and you start getting into the liquid range, well, we're no longer hardening our steel now or heating our steel. We're casting it, and then we got to come back and do heat treatment anyway. few interesting things happen in here. You'll see that there's a line that says the magnetic point. And one of the cool things that happens when you switch from ferrite to austenite is that your steel stops being magnetic. Because you've changed that crystal structure, it's the crystal structure of ferrite that makes steel magnetic or able to respond to magnetic fields. When you change that structure around and go to the face-centered cubic structure, your austenite is no longer magnetic. And I'm not going to recommend that you do this, but if you happen to be standing there and you've got a glowing piece of steel and you've got a magnet, try touching that glowing piece of steel to that magnet, and you'll know if you've reached the magnetic point and transformed everything into austenite, because you'll no longer have a magnetic material. You'll also hear these terms used a little bit, and again, I'm going off on an aside right here, but you'll hear these terms, austenite and ferrite, used with regard to stainless steels, because you can have austenitic stainless steels and ferritic stainless steels. Now, they have a whole bunch more alloys in them, and they have their own phase diagrams. Um, Iron and carbon really matter in there, but you've got nickel and chromium doing things in there too. And what happens is if you've got the right mix of nickel and chromium with your iron, you can actually trap the iron in an austenitic structure as you cool it down. And then you end up with a non-magnetic stainless steel. And that's generally, for most applications, a higher grade of stainless steel than the ferritic grades are. So if you're ever shopping for a barbecue and you want to know how long it's going to last, take a magnet along with you then and just tap it onto the high temperature parts of the barbecue. If the magnet sticks, then you've got ferritic steel, because ferrite is your low temperature form that is magnetic. But if the magnet doesn't stick to the stainless steel, then you've got a high temperature form, which is your austenite, which is non-magnetic. Anyway, that's a little off to the side, but just Jason's helpful tips for shopping for barbecues. And now I'm thinking about food. Okay, so we're just going to take a look at this little corner of the iron carbon phase diagram, because that really lets us focus our efforts and focus on what we're trying to understand. Okay, so just a quick review of some of the things we talked about. We talked about this phase called ferrite. It exists, the room temperature steel wants to be ferrite if we let it be ferrite. It's soft, it's magnetic, ductile, it's very pure phase, body-centered cubic crystal structure, and the carbon would love to be dissolved in the interstitial voids, but those small voids, they don't have room for the carbon in there. It's like trying to stuff volleyballs in with your basketballs. It just doesn't fit. Okay, now pure ferrite is not all that common. In fact, to get pure ferrite, you need to have steels that even when it's hot, okay, and everything's vibrating around and you've got a little more space in your interstitial voids, even when it's hot, up around 723 Celsius here, um, you can only fit 0.02% carbon in there. It's just not going to fit in there very much at all. So this range right in here is the only place where your steel would be made entirely out of pure ferrite. So there's a few other things that are going to fit into your room temperature steel. Now we talked about cementite being one of those, okay? And cementite is material that is Fe3C, okay? And that's called an iron carbide, and it's a very hard, brittle ceramic type substance. Ceramic's not quite true. There's technically a better name for that, but it's not held together with metallic bonds. It's held together with covalent bonds, and it is 6.7% carbon by weight. Now, the higher the carbon content in your steel, the more cementite you'll have in the steel, so the harder the steel will be. Well, a little bit harder, okay? Keep in mind we're talking tiny differences in the amount of cementite in there. We're going to do other things that make the steel quite a bit harder, but you will see a hardness difference when you take a look at that. In this region right in here, most of your cementite actually gets mixed with ferrite, and you form these fine layers called pearlite. Okay, so when our steel is trying to become ferrite, but it's got too much carbon in it and it needs to form some cementite, you end up forming what's actually a composite material that takes the soft ferrite and layers it together with the hard, more brittle cementite. And here's a photograph that you can see. Oh, my face is right over top of there. Let me just adjust that for a moment. And that would be, I'm going to turn my smiling face off here. And how do I transition that into pausing? Back in a sec. And we're back, and poof, there we go. Took me a minute to figure that out. Okay, down in this corner, this image shows layers of cementite in the dark material mixed with layers of ferrite in the light material. Now, this photograph has been, it's probably zoomed about 100 times in right there. And this has been produced by taking a sample of steel, slicing it, and polishing it, and then etching it. And you use an etchant that attacks the cementite more aggressively than it attacks the ferrite. So you can see that the black lines right here are the cementite. They've been etched away, leaving the ferrite behind. So in a lot of our steels, as you get more and more carbon into it, you're going to see more and more layers of cementite or a denser packed pearlite layer. Okay, and so this is actually what you'd see if you came right up and down the middle here with a eutectoid steel. There's no extra crystals of ferrite, no extra white crystals, and there's no extra crystals of cementite, which would show up as black chunks in there. You're just seeing 100% pearlite, this very super fine mixture of cementite and ferrite. Okay, let's see. Still recording. On to the next slide. Okay, now your austenite is up in the top part of the frame right here. There we go. And your austenite's right up here. And this is your hot part of the steel. You see we're up above 723 degrees Celsius right here. And depending on the concentration of your steel, you may have to go to a higher temperature than 723 degrees to get everything into the austenite range. Because right here, you're not 100% into the austenite range. You're in a slush zone, just like that. As the ice starts to form with salt in it, you start to get a little bit of slush forming first. Well, in here, you've got a mix of the austenite and ferrite right in here. And on this side, you've got a mix of austenite and cementite. So up here, though, you've got 100% pure austenite. All of the carbon is dissolved evenly throughout the material, assuming you leave it there long enough, okay? It's going to take a little bit of while. This doesn't happen instantaneously. The material has to heat up, and then all of the atoms are vibrating around in there. We use the analogy of, low temperature materials being like the opera and high temperature materials being like a nightclub. And it's very difficult to go get a drink at the opera when the performance is happening because everybody's locked in place. It's all cold. But at the nightclub where it's hot and hip and happening, everybody's moving around, you want to move across the floor, you just weave between everybody else and you go off to the other side of the club. You get your drink and you weave between everybody else. You come back and you sit down. You might get bumped around a little bit on the way, but at least you're able to get across the floor. Okay, so austenite right up here is our high temperature phase of the iron. And if it's glowing, it's austenite is a pretty good rule to think about with your steel. It should also be non-magnetic because our magnetic transition point is right in here. And by the time you get it glowing, you've transitioned from the body-centered cubic structure into the face-centered cubic structure. You've got those larger interstitial voids. They can hold the carbon in there, and you can diffuse the carbon out evenly. So all of that pearlite that existed down at low temperature because we didn't have room for the carbon, uh, that is now dissolved if you give it some time and formed a very even mixture throughout the solid iron. It's taking a long time for this to advance slides. Ah, here we go. Did I miss one in there? Right. So here's our ferrite slush zone right in here. So I was saying that, as you heat your steel, so down here you've got, you're starting out with a fairly low carbon steel. It is a mix of uh, ferrite with cementite, but mostly what you'll have is large crystals of ferrite because it's a low carbon steel, and then you'll have some little layers of pearlite, which is the mix of ferrite and cementite that is where most of the carbon is stored at low temperatures. As you start to heat that up, you come up into here and you start getting into the slush zone. Now, what this means is that some of the material starts to transition into austenite. Now, right at this point here, you haven't 100% transitioned into austenite because you're still in that slush zone. It's a mix of the two. So you come up right through here, and as things heat up, a little bit of austenite, a new austenite crystal, will start to grow. And as that austenite crystal starts to grow, it can absorb the carbon from the ferrite, from the cementite, so it can start eating up some of the pearlite that had formed in there. And it will start to grow bigger and bigger. And as you heat it up more, you'll have more crystals forming, and they'll be larger crystals, and they'll occupy more and more space until you reach this temperature up right here. And now your crystals have grown, and 100% of your structure has transitioned over to austenite. So in this region, you're perfectly into austenite. Again, you have to leave it here for a little bit because it does take time for the steel to have the austenite go through and absorb all that carbon. The atoms do have to physically move and transition through there. You'll notice that the slush zone only exists up to 8.83% carbon. This is where our 1080 steels come in, and they really don't have a slush zone in there. So they have some interesting behavior characteristics when they cool, and you'll see us refer back to this as a eutectic point. Okay. Um, and yeah, so let's take a look at the next slide right here. So on the other side of the chart, we've got a cementite slush zone right in here. And in this region, we're still going to transition into austenite because everything up in this region right in here is austenite. But what's going to happen as we go through this way, we're going to have some cementite form right in here. Okay, so well, the cementite's already formed down here, but what's first going to happen is some of the carbon is going to getting sucked into the austenite, and eventually, by the time we get up to the top, we'll have sucked all the austenite, uh, all the carbon out of the cementite and the pearlite, and distributed evenly across the steel into those interstitial voids in the austenite. And at this point right in here, our eutectic point, it doesn't pass through either slush zone. It just comes up in here. And at this temperature, new austenite crystals start to grow, and they start to eat up all of the carbon that's around them and all of the iron atoms that are around them. And you just grow new atoms, new crystals of austenite. Okay. Now, how do we know all this stuff? Well, let me take a look at my drawer down here. And that's my old wood identification lab. Somewhere in here, effects of carbon cooling, and there we go, my MMAT 376 lab from the good old days and material science at UBC. And you can see pictures in here of what this guy is doing right there is he's trying to come up with some beautiful photos that look something like this. Okay, as I hold that photo up to the screen on there, you can see the dark areas where we have perlite forming in there. The dark areas again are the ferrite. They've been etched away by an etchant. And the sample that you see right in here has been polished on these big spinning discs. You put it on the coarse disc and you go this way. You put it on a medium disc, you go that way. You put it on a finer disc, you go that way. You put it on a super fine disc and you go that way. You put it on an ultra fine disc and you go that way. And basically, you spend your entire lab over the course of an entire semester polishing samples of steel. And that was actually part of what people did at BCIT a few decades ago, was rather than just having a PowerPoint presentation where you listen to some guy talk about all this, you actually went out there and did it and you polished the steel. So maybe you're lucky, maybe you're not. But we've got other things to do with our time because all sorts of new technologies have come along since then. So anyway, this person right here is polishing a sample. You get it, mount it in a block and looking beautiful, perfectly smooth, etch it, and then pop it on a microscope and you get some beautiful photographs like I got 30 years ago. Never mind that. Okay, so here's what we actually see in some of those photographs. And so here is a 1040 steel. Now, keep in mind that just like doing our wood identification, we're looking at a two-dimensional image of a three-dimensional structure. So we've sliced through a lot of things. So where you see some different crystal sizes like this, it looks like a small crystal right in here. Well, it's quite possible that that's part of a crystal that's oriented vertically in and out of the page. And it's just as big as a crystal like this, but this crystal is oriented horizontally along the page, and so that we see more of this crystal just because of the angle that we've cut everything at. So you've got to keep in mind that you know this is a two-dimensional view of a uh, of a three-dimensional material. So let's come down here and take a look at our 1040 steel. What we'd see of nice, slowly cooled 1040 steel. Okay, and in here you'll see that we've got white, which is our ferrite. And then over here, we can't quite see the layers on this. Okay, if we zoomed in on it a bit more, we'd see a structure like this. But you can see it's kind of a gray scale right in there. That is our pearlite. Okay, now if we come over here and take a look at a 1011 steel, a 1011 steel has very, very, very little carbon in it. Okay, and right in here you can see it's almost all ferrite. You can see grain boundaries at the edge of each crystal along through here, but by and large, there's only chunks of pearlite right in here, and right in here, right in here. These dark bits are your pearlite. And if we zoom in even more on that, so this is 50 microns in scale. If we go down to like 2 microns down here, um, 2 times 10 to the minus 6 meters, so thousandths of millimeters we're talking about in here. You can actually see fine, fine, fine layers right in here. And um, the dark lines are the ferrite, and the little white lines or gray lines in between the dark lines. The dark lines are cementite, and the white lines in between are your ferrite. And this crystal right here is a pearlite structure because it's a mix of ferrite and cementite. Hey, if you're having problems keeping up with the words, you can hear my brain going, say the right word, say the right word. They're not words that we use in everyday conversation, so they don't always flow naturally. Um, But anyway, it's pretty interesting because you can actually tell a lot about the carbon content of a steel by looking at the image. So looking at this image of the 1011 steel, you can see, okay, well, we've got about that much um, Pearlite in it. But if we come and look at the 1040 steel, you can see that there's about 4 times as much Pearlite in there. And if I turn my talking head off right here again, there we go. Down in the bottom corner right in here, you can see a 1095 steel, and you don't really see any of the big white crystals anymore. You see little bits of whiteness in here where the uh, uh, where you're looking at the layers of ferrite inside the pearlite, but everything in here is pearlite with little chunks of cementite added in right here, pure cementite forming right in here in those really dark areas. So you can actually go through and you can do a statistical sampling technique to figure out what fraction of your image is going to be ferrite, what fraction is going to be pearlite, and if you've got high carbon, you can go through and figure out what fraction is going to be your cementite. And we know what the concentration of carbon is in each of those. So if you know how much you've got of ferrite and how much you've got of cementite, then you can go through and you can calculate what your overall carbon content for the steel is just by taking a look at it. There's other techniques that involve blasting beams into it and everything like that. And of course, there's always the spark test. But if you wanted something more accurate than the spark test, you could come along and you could spend many hours polishing up your steel sample, look at it under a microscope. Oh, I forgot to say etch it, look at it under a microscope, and then go through and do a bunch of math on it. And you could figure out exactly how much carbon was in your steel just by the way it looked. So that's actually kind of cool stuff, I think. There we go. Next slide. So what happens and how does this happen when we do our cooling? Okay, so in the event of low carbon steel, we're going to start cooling from this point right in here. Okay, you can see I've got a little yellow dot over top of it. And so this is something we're going to be doing in our lab. We're going to take low carbon steel, we're going to take medium and high carbon steels too. We're going to heat them up and we're going to let them soak into the austenite range because like I say, it takes time for the carbon to get moved around and it takes time for each of those uh, cells, each of those crystals to transition from one phase to the next. But here's our 1020 steel. Now our 1020 steel works up and down this line right here, and it works on that line because that line is the line for a 0.2% solution of carbon in iron. Okay, higher percentages of carbon and iron, we keep moving over this way until we reach 2% right up and down over here, and we no longer pay attention to that because anything beyond that is actually a cast iron, and similar principles apply, but we're just focusing on steel. So, okay, so we're heated up and it's heated all the way right up in here and it's glowing. Actually, at this temperature, it's probably glowing yellow or at the very least a good solid orange. And we leave it there for a while. And if we leave it there for a longer period of time, then it's going to grow bigger crystals. And if we only leave it there for a little while, then it's not going to grow the crystals of austenite quite so large. So keep in mind, as we heat it up, we transition through this zone and austenite starts growing usually at the grain boundaries of the old crystals, which is one of the reasons why heating this all the way up here, if you've work hardened your material, and you may recall doing this to the copper in our tensile testing lab, is we took our copper and we heated it up until it was glowing red hot, and the work hardened copper that we'd stretched grew new crystals that didn't have any history of work hardening, so when we cooled it back down again, our copper was nice and soft. With the steel, we might have a little bit of different experience depending on how we cool it down. Okay, so let's take a look what happens. Now we're going to cool that down a little bit. And we're going to come down right here. And now we've entered the slush zone. Okay, now inside the slush zone, we've started to have crystals of ferrite start to form. So now we've gone from austenite, and the steel is thinking, okay, well, I'm cooling down, time to start forming some ferrite. And as the ferrite starts to form right in here, the ferrite is very pure. And as it forms, it squeezes the carbon out. And what it does is that starts to increase the concentration of carbon in the remaining material. Okay. I once used an analogy that's probably inappropriate for school use, but not incorrect. The analogy where I sort of compared it to ethnic cleansing. And I know it's really bad, and I get that. And I actually never used it with my high school classes because I didn't know if any of my students were refugees or whose families had been refugees and fled, something like that. But what you can think of is when the ferrite starts to form, it forms a very pure community, and it doesn't like to have the carbon in it. So as those ferrite crystals start to get bigger and bigger and bigger, they start excluding more and more of the carbon, increasing the concentration in the surrounding environment. And then eventually, your concentration of carbon in the surrounding environment gets as high as it can reach when you're right down here, and you've cooled down to this point, and you get a mix of the ferrite locking in with the pearlite surrounding it. It's a horrible analogy. I'm feeling guilty that I even mentioned it now, but it gets the idea across that the carbon is getting squeezed out by the ferrite. Maybe I should use gentrification. Housing would be, eh, still wouldn't work in the high school. Got to be careful about what you talk about. People misinterpret things. Um, so crystals of pure ferrite will appear at the austenite grain boundaries, and as you ferrite expels the carbon, you increase the carbon concentration in the surrounding austenite, and you keep coming down and getting cooler and cooler. And now we're down here, and we've almost finished forming all of our ferrite. And we're just about to make this final transition into what's going to be our final stage of the transition process. And right now, we've squeezed out enough carbon that everything that's not ferrite right now has a much higher concentration of carbon. It's sitting right out here, and then we jump over that edge right there, and we'll have some of our material will be pure ferrite, and that'll be right here, and some of the material will be pure pearlite. Where'd my mouse go? Pure pearlite, which is what happens when you cross the line right here at the eutectoid. Okay, and so basically, the more carbon you have in your steel, you start out over here. Your transition into ferrite starts at a lower temperature, and you get a higher percentage of your material coming out as pearlite because you've got more carbon to deal with. And now we're down here, we've crossed over the line. Now the final transition to go from right here to right here, just like it did heating up, going down, it needs time to have that phase transition take place. And when you have that phase transition, it will actually give off some energy, slowing the cooling even a little bit more. So just like you'll notice that it takes a long time for water to form into ice, that's because the water has to give off a lot of energy to form ice. And same thing right here, you'll pause a little bit as you go through there. Now, if you really want to rush that, we'll take a look at ways that you can speed through there a lot quicker by taking your sample and throwing it in water and agitating it around and shaking it up. And there's all sorts of things you can do to cool your samples quickly. But anyway, if you cool it down nice and slowly, which is what we're talking about right now, you'll get the most organized, calmest, lowest energy, softest, least brittle, most ductile structure that you can possibly get. And sometimes you want to actually take many, many minutes to hours to pass through this zone right here and then complete all the cooling right down there. And that is called annealing your steel. That will get rid of any heat treatment that you've done it before and set it back to its softest state. So here's pictures of what starts to happen in there. Okay, at high temperature, we're 100% austenite. These yellow things are austenite crystals. They have an even distribution of carbon throughout them because the carbon's had time to diffuse throughout the material. As you start to cool down, at the grain boundaries, which are our high energy sites, little bits of ferrite start to grow. Okay, now the little bits of ferrite are very, very pure iron. They've got no carbon in them to speak of, so they're squeezing that carbon out into the surrounding structure, increasing the concentration of carbon in the remaining austenite. As these crystals get bigger, well, they're still very pure and they cool down here, and you get the surrounding material has its carbon concentration continue to increase. That's why I've drawn a slightly darker shade of yellow. And now when we make this final transition right here, our crystals of ferrite have grown as large as they can based on the thermodynamics of the material. We've now passed through this point and transitioned right in here. The concentration of carbon in these little remaining areas that haven't been crystallized by the ferrite are about as high as they're going to get, because this is going to form into pearlite, which is that very fine mixture of ferrite and cementite. So the little black streaks that we see in here are going to be hard and brittle, and the ferrite that runs between them is going to be soft, but the combination of that is going to give us a composite structure. The ferrite crystals right here will be very, very soft and very, very ductile. This is why your lower carbon steels, even without any heat treating, will be slightly softer and slightly more ductile than your high carbon steels, simply because there's more cementite in the high carbon steels, and that cementite is there in the form of pearlite. All right, now high carbon steels, um, similar things happen. You heat it up and you start out way up here where it's hot and everything is 100% austenite with carbon evenly diffused throughout it. And then you start to cool down here a little bit. And now the carbon's sitting there saying, well, I don't feel so good about being in some of these interstitial voids. I've entered a slush zone right in here. And in this slush zone right in here, instead of having low carbon ferrite start to form, what you've got in here is high carbon cementite starts to form. And so as this austenite starts to squeeze that out, the cementite is also a very pure structure, but it needs a lot of carbon. So it starts to suck carbon out of the surrounding austenite so that it can keep forming cementite. And as you come down this way, your remaining material slides down this track right here. Whereas the remaining concentration increased along this track right here, this one, the remaining material slips down right here. You keep getting these high concentrations of cementite forming. And then as you come down here, you eventually reach the transition temperature, and what's left right here translates straight into pearlite. So depending where you come through on here, if you've got a higher concentration of carbon, you'll come down here and you'll have a lot more cementite growth before your pearlite finally transitions. And if you're just only a little bit on this side, you'll have a little bit of cementite growth before your pearlite transitions. But on this side of the phase diagram, anything above 1080 steel is going to be a mix of pearlite and cementite, because the cementite will form first due to the high carbon, and anything on this side will be a mix of pearlite and ferrite, because the ferrite will form first due to the low carbon right in here. And if you go straight down the middle, you get eutectic cooling. And so our eutectoid steel comes right down through here, and you'll have 100% pearlite because there's no slush zone. So there's no ferrite forming first. There's no cementite forming first. It's just come down here and bang, you've got cementite. It still takes a while for that to happen. And if you cool it too rapidly, there won't be time for cementite to form. And when you don't leave time for the cementite to form, that's where we start to actually get into what we call hardening steel. Everything we've talked about right now, even though I've used the term hard and soft and ductile and brittle a lot, this is not actually hardening steel. This has all been about annealing steel, undoing the hardening that happens in steel. So it's only when we start to quench things and cool them down rapidly that we really get into the part that makes steel such a cool material, because that is some serious hardening happening. Now, everything we see here is important. Don't get me wrong. It is important to know that a higher carbon steel, even after annealing, will be slightly harder than a lower carbon steel because it has more cementite in it, usually in the form of pearlite. Okay, enough big words. Um, you don't have to fully understand this after 1 hour of me going on about it, but it would be great if you're starting to get comfortable with the idea that we've got two phases of steel that we're going to talk about: the high temperature phase, austenite, and the low temperature phase, ferrite. That in the high temperature, we can distribute the carbon evenly throughout the steel. And in the low temperatures, we cannot distribute the carbon there because low temperature ferrite squeezes out all of that carbon. That we've also got a phase called pearlite, which is a mix. It's not really a phase, but it kind of acts like one. It's a mix of the cementite and the ferrite, and that occurs at a very specific concentration right in here and creates layers or laminar structure, which combines the hard and brittle properties of cementite with the soft and ductile properties of ferrite. So you will get differences in hardness, you will get differences in strength, even in the annealed steels, annealing being a very slow cooling process that allows time for all of the atoms to redistribute when you go through a phase change. We're going to do that. We're going to talk about that. Next time back, we're going to talk about what happens if you don't give time for those structures to go through the phase change. What happens if you rush it? Well, that's where hardening comes in, and some pretty cool magic that people have figured out a long time ago. Thank you very much. And there's other resources that you'll find online. Feel free to look them up because this is an important concept. It explains not only how to harden a steel, but also things to watch for and some of the negative consequences of not welding your steel properly, because even when you're not trying to harden a steel, sometimes you are if you're welding it. Oh, did I run out of screen? Oh, bye. I'm not on the screen anymore. Where am I? How do I say bye? Just a minute. There we go. Bye. Ooh, camera lag. I think I need to go home and eat.